lecture number 8, VSPER Theory. So we're going to expand on this idea of Lewis structures, and we're going to start taking what we call in the Lewis structure a two-dimensional representation and start extrapolating that into this 3-dimensional space. And the way we're going to use that is this valence shell electron repulsion theory, or VSPER theory. So this VSPER theory is the way we're going to predict from this two-dimensional Lewis structure that we draw the 3-dimensional shape of the molecule, either a simple molecule like we've drawn or a much bigger molecule, as well as some bond angles and other information. So this VSPER theory is the valence shell electron propulsion. So the shape is really dictated by those electrons, the paired or shared or unpaired, pushing away the other electrons. And we're always going to be talking about in this theory based on some central atom. So we're going to look at the central atom, the one in the middle, and talk about what environment surrounds it. And we're going to look at something here. We're going to talk about a class of a compound, or just a general idea, the number of atoms bonded to that central atom, the number of lone pairs on that central atom. Sometimes those are going to be the same, sometimes they're not. If there's lone pairs, then the number of bonded atoms are going to be, I guess, sometimes it'll be, the lone pairs will be 0, sometimes it won't. How the electrons themselves are arranged, both shared and lone pairs around that atom, and then what that corresponds to as far as the molecular geometry. And we'll see there's 5 major sort of base geometries that everything's based on. Right? So we're going to look at these 5 sort of foundations and then change from there. This first one we'll look at is if we look at the central atom and there's 2 regions around it. If there's only one other atom, right, that's going to be a linear molecule. So if there's 2 atoms together, no true central atom, that's going to be a linear arrangement. Don't really need to talk much about that one. But if there's 3 atoms present, right, then we're going to have this central atom, and then on that there's going to be 2 possibilities. Right? And this is what we call an AX2, so there's one central atom, 2 things bound to it. The number of bonding groups is going to be, again, 2. It only can be 180. The farthest those electrons can be from each other is 180 degrees. So we're going to end up with a linear arrangement. Fairly straightforward, right? Those electrons are repelling each other away. We're going to end up with 180 degrees. If we go to the next one, where we have a central atom and then 3 things bound to it, right? The furthest away they can get is 120 degrees, all in the same plane. So this is what we refer to as a trigonal planar arrangement. Right? So we're going to look at that. The furthest arrangement, or those electrons can get away from each other, is that 120 degrees trigonal planar. If we have 5 things bound around that central atom, or excuse me, 4, then the base arrangement, if those are all atoms, those are going to be what we call tetrahedral. So it's going to look something like this, right? Where we form a tetrahedron, a 4-sided solid, if we connect the atoms together, right? 4 bounded atoms, that base group is called a tetrahedron. If we have 5 things bound around the central atom, we are going to get this, right? Again, we have a 3-sided base here. If we completely enclosed it, then we were going to get a bottom, it's a triangle, and it's going to be, up to the top, it's going to be a pyramid. So it's trigonal pyramidal, but there's 2 of them because there's the one on the top and the one on the bottom. So this shape is called trigonal bipyramidal, right? When we have 5 things bound to the central atom. If we have 6, now we get this shape. And this shape we're going to call octahedral. There's 8 sides to this, or 8 faces on this enclosed surface. So this is the octahedral. So if we have 3 things bound to it, we call that trigonal planar. 4 things, tetrahedron. 5 things, trigonal bipyramidal. And 6 things, octahedral. Right, so this base thing where we have no lone pairs, all bonded atoms are fairly, it's one of those 5 categories. Once we start introducing lone pairs, what we're going to see is this shape is going to change, but those electrons are still present. Right? And they're still going to take up space, and they're going to actually, they take up more space than if they were bound together, because they're free to move around. They're going to take up more space, even though they're really small. So that's going to change our shape slightly, but the base electron geometry, if we will, is still going to be one of those 5. So what we're really going to do when we're talking about this VSPER theory is we're going to count places where we have electrons around the central atom. That's going to give us this base formation. It's going to be one of those 5 different arrangements: linear, trigonal planar, tetrahedral, trigonal bipyramidal, or octahedral. If some of those aren't occupied or are lone pairs, then the shape is going to be based off of that, but it's going to be slightly different, and we'll look at those individually. So if we take that first example, as you can see here, if we have a central atom that's bound to 2 things, if one of those is a lone pair, we're going to end up with a linear species anyway. So that really doesn't change. If we look at the trigonal bipyramidal, this second one in the middle, if we have one of those lone pairs, right, the lone pair is going to be not going to appear there. So if we have the trigonal planar species, right, if one of those is a lone pair, which means we won't see it because it's much smaller than those atoms, we're going to get this, which is best described as bent or angular. I think the book's calling it V-shaped. I always refer to it as bent. Right? And if this angle here originally started out at 120, this lone pair is going to take more room, which is going to constrict that, and it's going to end up being less than 120 degrees. Right? So anytime we have a lone pair, those are going to take up more space, which is going to constrict the rest of those angles. If we look at the tetrahedral arrangement, if we have 4 things bound to it, we have tetrahedron. If one of those is a lone pair, right, in the tetrahedral arrangement, the bond angles here is 109.5 degrees. If one of those is a lone pair, right, we end up with this, which is a 3-sided pyramid, which we would call trigonal pyramidal. Right? Again, because this lone pair is taking up more room, this is going to constrict, which means our bond angles are going to be less than 109.5, somewhere around 107. Right? That's going to be less than 109.5. If we take 2 things away, or we have 2 lone pairs, now we end up with this. Right? The electrons would still be arranged tetrahedrally, but the molecule itself is going to be bent. So if we have 4 places of electrons around our central atom, tetrahedral electron geometry, and the molecule itself, if there's no lone pairs, will be tetrahedron. If there is 1 lone pair, trigonal pyramidal, 2 lone pair, bent. If we look at our next species, this trigonal bipyramidal, where we have 5 areas of electrons around the central atom, we have 2 different sets of bond angles. The ones what we call around the middle we call the skirt. It's essentially all in the same plane. Those bond angles here is going to be 120 degrees. But this top one to that skirt is 90 degrees. So in this arrangement, in the trigonal bipyramidal, we have 2 different bond angles, 120 around the skirt, 90 from the skirt and the top, and 90 from the skirt to the bottom. Since if we have a electron or a molecule that has a lone pair, a single lone pair, they want those lone pair electrons, as we've said already, take up the most space. So we want to put them in this structure where they have the most room. And we see that's actually along this skirt here. Right? So if we have a lone pair, we're going to end up with a lone pair around the middle. And this is best described if we flip it on its side and do this. That's a seesaw. This is a seesaw shape. Sometimes you'll also see the term distorted tetrahedron, but I prefer seesaw. It's just more fun. Right? Again, now those electrons are going to compress the rest of these bond angles, so the bond angles are going to be less than what they started out at, less than 90, and a less than 180, or excuse me, 120. Right? If we have two lone pairs, again, we're going to take it from around the middle, and we're going to end up with something that looks like a T, which we cleverly call T-shaped. Again, our bond angles are going to be less than this, which was 90, so those are going to be less than 90. If we have three electrons, now we end up with something that is linear. Those electrons are all going to be around that middle section, and these are going to be as far apart as possible, which is 180 degrees, which is linear. So again, if we have 5 areas where we have electrons around this central atom, if they're all connected or shared with some other element, then it is going to be trigonal bipyramidal. 1 lone pair, it's going to be seesaw. 2 lone pairs, T-shaped. 3 lone pairs, linear. But it's all based on this original electron arrangement of trigonal bipyramidal. If we looked at the octahedron, again, now if we separate 360, this sort of middle skirt area, by 4, that gives us a bond angle of 90. So all the bond angles in the octahedron are actually 90 degrees. So when we start removing electrons, it's not going to be as particular where they go, and in fact there's free rotation, so we're going to end up with the same arrangement no matter where we take it. If we take one off, take it off the bottom here, then we have a 4-sided surface on the bottom, or a square, but it's a pyramid, so this shape is called square pyramidal. Again, that lone pair are going to take up more space, so our bond angles are going to constrict, and they're all going to be less than 90. If we have 2, now we see that the remaining, to give those the most space, that would be on the top and the bottom, the 4 that are remaining are all going to be in the same plane, and they're going to form a square. So this shape is called square planar. Right? Now the compression from these electrons is going to be offset by these, so the bond angles will stay at 90 degrees. If we have 3 lone pairs, take one off, we end up with T-shaped again. If we have 4 lone pairs, we end up back at linear. So when we're looking at these molecular geometries, we're always starting by looking at where electrons are around that central atom. That's going to give us one of these 5 possible arrangements. And then from that, we look at that arrangement, take some electrons. If there's a lone pair present, that one goes away, and we see what the resulting shape looks like. So in general, when we look at this, the first step in these Lewis, or predicting the molecular geometry, is going to be predicting or writing the correct Lewis structure. Again, we've been practicing that. It's probably the most important. If you do that part wrong, then the shape, it doesn't really matter. Right? You're going to predict the inaccurate shape. We're going to count the number of electrons around the central, places where you have electrons around the central atom. Multiple bonds will count as one place. So for a double bond, will count as one place where we have electrons. And then based on how many that is, it's going to be one of these base electrons. If they're lone pairs, we ignore them in the 3-dimensional shape, and we predict then the actual shape. So if we look at this molecule here, excuse me, we have around that central, that sulfur, that central atom, we have 3 areas where we have electron density. So our base electron geometry is going to be trigonal planar. One of those areas is a lone pair. So from that trigonal planar arrangement, one of those disappears, and we end up with something that is bent. The bond angles here are going to be less than the base, which is 120. So this would have bond angles less than 120 degrees. Now we can go back and talk a little bit more about, now that we can predict 3-dimensional shapes, we can talk about electronegativity differences. Before, we've talked about between 2 atoms in a bond. Right? Now we have multiple atoms bonded. So we can again talk about this idea of these polar bonds, but only extend it beyond just a single bond and into the whole molecule. And when we have that, we're extended across the whole molecule, we're going to call those dipole moments. We'll still use the same representation we had before. The more electronegative, or the direction that the electrons are primarily moving, gets the arrow and is partially negative. The other side, where the electrons have sort of moved away from, is going to be partially positive or get the plus sign. So what we're going to see is when we look at this single bond, we're going to then sort of sum up all of the bonds across the molecule. So if we look at the ammonia molecule here, in H3, we see that it is the electron geometry is tetrahedral. The molecular shape, one of those is gone, is trigonal pyramidal. And all of those in ammonia, the nitrogen is more electronegative than the hydrogen, so all of those electrons are going to be moving up towards the nitrogen. So the overall dipole moment on top of the molecule, where we have that lone pair, is going to be negatively charged, partially negative charged, and the bottom of the molecule is going to be partially positive. If we change that to nitrogen trifluoride, where we replace those hydrogens with fluorines, now fluorine becomes more electronegative. Those electrons are going to be moving down towards those fluorines, so our dipole moment actually switches. The overall dipole moment is pulling electrons towards the bottom of the molecule, which leaves the top of the molecule partially positive. So we're going to extend this idea of polarity based on electronegativities not only across a single bond, but over the entire molecule to predict these structures.
Dad, I done did it.